Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 24 on partial fractions.
The previous 3 lessons have solved integrals by means of running differentiation rules in reverse. We're going to change our perspective now and give an introduction to methods based on algebraic simplification. The broadest and most generally useful such method is called the method of partial fractions.
In this lesson, we'll look at certain algebraic methods for simplifying integrands. Indeed, certain integrands respond well to a pre-processing step. This is especially true for rational functions, ratios of polynomials. For example, if you are asked to integrate 3x squared minus 5 over x minus 2, then naturally you would perform the polynomial division and rewrite this as 3x plus 6 with a remainder of 7 over x minus 2. And while the former integral seems intimidating, the latter integral is simple. 3x gives 3 halves x squared, 6 integrates to 6x, and 7 over x minus 2 yields 7 log x minus 2, and then add the constant. Now, this is a trivial example, but what happens when you have a higher degree denominator in your rational integrand? We're going to rely on a certain result from algebra, which states the following. A rational function, p of x over q of x, where the degree of the denominator is greater than the degree of the numerator, and for which the denominator has distinct real roots, r sub I. That is, we're looking at an integrand of the form polynomial p over x minus r1 times x minus r2 times etc., all the way up to x minus r sub n, where q has n distinct real roots. Then this can be factored or decomposed as a sum of constants, a sub I, over quantity x minus r sub I. This fact is something that we're going to take for granted. We're not going to prove it, but we're going to use it extensively. This integral of p over q seems very difficult in general. However, the right-hand side can easily be integrated since all of these a sub i's are constants. Then we get simply logarithms. Now, what do we do to come up with this decomposition? How do we determine these constants, a sub I? This is sometimes called the method of partial fractions. Let's look at an example. Simplify 3x minus 1 over x squared minus 5x minus 6. We can factor the denominator as quantity x plus 1 times quantity x minus 6. By our algebraic fact, we know that this must be a1 over x plus 1 plus a2 over x minus 6. For simplicity, let's call these constants a and b instead. Now, to determine a and b, we're going to multiply out the right-hand side, put it over a common denominator, where we'll obtain a times quantity x minus 6 plus b times quantity x plus 1 in the numerator. And now we're going to expand that multiplication out and collect terms so that the first degree coefficient is a plus b, and the constant coefficient is b times 1 minus 6 times 6a. Now, these must match up with the coefficients of the numerator, 3x minus 1. If we have two polynomials that are the same, then all of their coefficients must match up. And so we see we are reduced to two equations in two unknowns, namely a plus b equals 3 and b minus 6a equals negative 1. Now we can solve such a linear system of equations for a and b. It might take a bit more work than I'm willing to put on this slide. So let me show you a more direct method for computing a and b. If, as before, we write out 3x minus 1 equals a times x minus 6 plus b times x plus 1, then instead of expanding and collecting, we can do the following. We can say this is a true statement, and it must be true for all values of x. Therefore, it must be true at x equals negative 1. What happens when we substitute that in? On the left, we get negative 4. On the right, we get a times negative 7 plus b times 0. And we've eliminated that variable from consideration. Solving, we obtain a is 4/7. Likewise, if we substitute in x equals 6 into the above equation, we get on the left-hand side 17. On the right-hand side, a times 0 plus b times 7. We therefore have eliminated a, and we can conclude that b is 17/7. And I'll let you check that these two satisfy the two equations in the lower left-hand corner. Now, let's put this method to work. Compute the integral of x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. Factoring the denominator gives us x, quantity 2x minus 1, quantity x plus 2, all multiplied together. Now, we hope to split these up into a over x plus b over 2x minus 1 plus c over x plus 2. Let's color code these and then multiply everything out and see what we get. A times 2x minus 1 times x plus 2 plus b times x plus 2 plus c times x times 2x minus 1 must equal the numerator of the integrand, x squared plus 2x minus 1. Let's use our direct method of substitution. First, we'll substitute in x equals 0. When we do that, we eliminate all of the terms except the one involving a. We obtain negative 2a equals minus 1. Solving, we get a is a half. Likewise, if we substitute in x equals 1/2, we eliminate all the terms except for the b, which we solve to get b is 1/5. What's our last root? If we substitute in x equals negative 2, then we obtain a value for c of negative 1/10. Substituting these coefficients back into the integrand gives us, for our integral, the integral of 1/2 over x plus 1/5 over 2x minus 1 minus 1/10 over x plus 2. These are all going to be logarithms. We're going to get 1/2 log of x plus 1/10 log of 2x minus 1, being careful with that 1/2 coefficient, minus 1/10 log of x plus 2. Let's put this to use in a differential equation. Consider the deflection x as a function of time t associated to a thin beam that we've applied a force to. The question is, how does this deflection evolve Well, if the load is proportional to a positive constant, lambda squared, then one simple model for this beam would be dx dt equals lambda x squared minus x cubed. We can factor that as x times lambda minus x times lambda plus x. And now, applying the separation method, we get on the left dx over x times lambda minus x times lambda plus x. On the right, dt. Integrating both sides prompts the use of a partial fractions method. I'll leave it to you to show that the coefficients in front of the terms are, respectively, 1 over lambda squared, 1 over 2 lambda squared, and negative 1 over 2 lambda squared. So that when we perform the integral, we get a collection of natural logs with coefficients in front, namely log of x minus 1/2 log of lambda minus x minus 1/2 log of lambda plus x equals lambda squared t plus a constant, where I've moved the lambda squareds to the right-hand side for simplicity. Now, what we would do next is try to solve for x as a function of t. This looks like it's going to involve a lot of algebra, and I'm not really in the mood. So let's use linearization and solve for the equilibria to see if we can understand what's happening. If we plot x dot versus x, we see that there are 3 roots. One root at 0, one root at negative lambda, and one root at positive lambda. By looking at the sign of x dot, or by linearizing the right-hand side of the equation, we can see that 0 is going to be an unstable equilibrium. That makes physical sense. If you're compressing the beam, if it were perfectly symmetric, then it would not deflect. However, that situation is inherently unstable. And if you start off with just a little bit of deflection in either direction, you will quickly move to one of the stable equilibria at lambda or negative lambda, depending on which side you buckle. Now, there are some complications involved with applying the method of partial fractions. We've assumed the existence of real, distinct roots. That is a bit of a luxury. In general, you don't have that. Sometimes you have repeated roots, something of the form a polynomial over x minus a root r to the nth power. This decomposes, but it decomposes into something a bit more complicated. There are n terms. Each is a constant over x minus r to some power, ranging from 1 up to n. Now, all of these individual terms are integrable, but some might take a little more work than others. What is potentially worse is complex roots, where you don't necessarily have real roots. Let's say we look at a polynomial over a quadratic, ax squared plus bx plus c. Then if the discriminant, b squared minus 4ac, is negative, we have complex roots. This does break up, but it breaks up into a linear polynomial in the numerator, and then the quadratic in the denominator. And if you have repeated complex roots, well, then it gets even more difficult still. All of these examples are doable, but very cumbersome, and I'm not going to test you on these in this course. In the end, it's really just algebra. And in the end, it's really just roots. The roots control everything, whether they're real, whether they're complex, whether they're distinct or repeated. As we saw in the example of the buckling beam, the roots have physical interpretations in differential equation models. Always pay attention to your roots, not just in calculus when trying to solve an integral, but in differential equations, or even later still, when you take linear algebra, you will see that the roots influence everything.
We've seen in this lesson how algebraic methods can be incredibly helpful and incredibly complicated. We're not going to descend any further into that underworld of integration techniques. Rather, we're going to turn our gaze to a new character in our story, that of the definite integral.